surface example, and then get into some more kind of esoteric aspects of the idea of dispersion heads. And one of these two examples, and there's others that are out there, and it's certainly important to Australia, is the idea that metals at depth find their way to the surface. And whether it's ion exchange or evaporation-driven processes, or in the case of things like tin or arsenic, you can actually methylate it, create a gas, which would transport it to the surface. And then from there into the idea of how we get at these in terms of weak leaches. A couple of examples of metal-specific things, which are actually quite rare. So in the Bathurst mining camp, kind of just it's, you know, we've got massive sulfide, copper, lead, zinc near surface. It's undergoing weathering reactions, so it's kind of a gimme in that regard, that it should be something easy to find. And when you're looking at kind of bacterial mineral interactions or leaching of metals, then if you've got outcrop or something near the surface, then you guys have found it already, right? There's very little that's near the surface that hasn't been discovered. The one exception to that was Voisey Bay. It was in Newfoundland. They said it was geologically inactive. You'll never find an ore body there. And it was a geologist joyriding with a buddy in a helicopter said, it's all that, it was a rusted, it was a Gossan. It was a Gossan in Newfoundland. They went down, broke off a chunk of it, brought it back, and it was economic. Largest nickel mine in Canada, right, on a joyride. But most of it's been found. In the case here, we've got a couple of examples, the idea of water analysis that they've done. And in this case, there was actually a seep that was identified. So it would be like an acid leachate or something like that. And you cross over that boundary and your zinc goes from 0 to 8 ppm. So a real defined thing, and then the question is, where is that seep coming from? And if you track it, there should be some influence or input of metals. The other two plots, one looks at lead, and it's got a partial extraction, which is a weak leach. So when you think of those iron oxides and manganese oxides, the fresh hydrated minerals that we've been talking about, other base metals will bind into those mineral structures, but being something that's very hydrated, you can add just a little bit of acid and pop off metals, right? You're competing for reactive sites, and you can extract it versus a total sediment, which is a harsh leach, something all the way to perhaps aquaregia, right, where you can dissolve gold. So in the case of the lead, the total sediment and the partial extraction are the same. And what this argues is that most, if not all, the lead is in this hydrated, very available form, and certainly bioavailable, versus something like indium, which really doesn't undergo biogeochemical cycling, and there's very little in the weak leach, and the high values here in the sediment. And what that tells you is that in addition to the seep, adding metals into the system, that there has to be mass wasting, an actual transport of minerals into this stream to produce this kind of anomaly. So what are your thoughts on this as an exploration tool? Okay, we've got metals that are washing in here, kind of the idea of solubilized metals, things like lead and zinc. Okay, there's a seep that seems to be bringing that in. How reliable are seeps? In natural, so in this case, reliable in that we produced a signal. Okay, so we got a signal in sediment, and we got a signal in water. How reliable are seeps just in general? Anyone, my experience with them was not great in Arizona. That we had seeps that were listed on a map where we were getting our drinking water. And some had water, and some were just drip, 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 and we're just, we're in 40 degrees C. I've got the arches of collected so much water that my arches collapsed, and I'm bruising all along the bones. So every time we stopped, we had 10 pounds of samples. And we hiked 40 kilometers down kind of a slot canyon. And when you're near the bottom and there's no water, it's a real drag, because the creek is just mud. It's like chocolate milk, but not good. And so we're trying to settle it and filter it and iodine and treat it, because that's what we had to drink. That was our only choice. So these things, if it's flowing and it's got metals in it, you're golden. If it's not flowing, then the idea of sampling water here, you wouldn't get anything. In the case of sediments, though, the idea of them acting as a reservoir, that, and certainly the concentrations are an order of magnitude higher. So from a few ppm up to, kind of a couple of thousand ppm, that the sediments are enriched in metals. So if you're adding in low levels of metal in the water over time, that the sediments downstream will become increasingly enriched in those same metals. And we looked at those processes, that within this massive sulfide, you're going to have pyrite as well. So you're going to have iron oxides and bacteria that oxidize iron oxides. So in this environment here, if you've got iron oxidizing bacteria, then the first hydrolysis product, right, the rust, will bind up lead, will bind up zinc, and we'll pull it down into the sediment. So if you sample the sediment, then you've got higher values, and you've got something that, it doesn't matter whether that seep is flowing, you're going to get that signal. Okay, so something a little better. And throughout Northern Ontario, our colleagues in the Ontario Geological Survey, and they literally go around in a helicopter, hit a lake, and within 5 minutes of the floats hitting the water, they've thrown down a dredge, they've grabbed a sample, it's into the helicopter, they're bagging it and closing the door as the helicopter is taking off, and they're going from lake to lake to lake. And just as reservoirs of everything washing in on those little basins and looking at metal distributions. So if you look at, kind of some of the images we've had and this is an iron oxide persisting arsenic we talked about earlier from the mine site, but this is the same sort of thing, that you're going to form minerals on the bacterial surface. And this was an example of passive mineralization, but you could put in, active mineralization. So the iron oxidizing bacteria or manganese oxidizing bacteria, if they happen to be present. In terms of the sediment, if there's poor water and things flowing through the sediment, you could support sulfate-reducing bacteria. So all of the active and passive processes that you've looked at in terms of forming minerals can enrich metal within streams and within stream sediments down gradient from metals washing in. And the idea that here's a cell, here's another one, probably one there, but you get aggregates of things. You load up bacteria with minerals, they get heavy, they sink. So, and this is that idea of the bacterial polishing of water, that is used in water treatment systems, that they'll bind metals, they'll help flocculate and settle those metals, so your sediments become increasingly enriched in minerals downstream. So it's a nice material to sample. And this is the stuff that's fairly straightforward, and you can track up the stream, and you've got an anomaly, and and it disappears. So, well, if you look left all right, then we'll see what we can find out there. The Romans did that. Okay, the Iberian Pyrite Belt is something like 48 world-class ore deposits. The Romans found 47 of them. And the river there it's Rio Tinto, it's just pure iron oxide. And they were literally walking up the stream until the oxides disappeared. Literally, they went up into the hills, they found the Gaussens, and they started mining down. Okay, so an early stage in terms of sediments that are enriched in metals. In that case, it was macroscopic. They had a beautiful phenotype in that iron oxide. The stuff that's a little more esoteric is the idea that metals and minerals can come from below to the surface. And this gets into it's controversial. It doesn't always work. And it works in a variety of climates and a variety of regimes. So this is the Cross Lake study area. It's near Timmins in Northern Ontario. What you're looking at here, 6,000 years ago, it was under a kilometer of ice. So all the topsoil, everything that was there was scraped down into the US. Okay, and as the glaciers retreated, they deposited lake sediments and clays and new materials. So the soil here is only 6,000 years old, young by Australian standards. So here's one that we'll take a look at. And here's just a photo of it. We've got logging roads. It's just kind of typical forest. This is kind of a nicer area. The person is wearing a bug net because there are mosquitoes and black flies and deer flies and anywhere out there. You go off, we're on a nice little high here to work, but you go off of it, you're basically into bog. My OGS colleagues, they hate working in the summer. It's like, why are we coming out in the summertime? It's like, well, it's biologically active. He'd prefer to be out there in January, -30, with a snowmobile. It's like you can dress and stay warm, but it's hot and we're trying to hide from the bugs. So we've got nice soils that are developed here that are within the last 6,000 years, and there are metal signatures that have come from below through 10 meters of clay and lake sediments and streams up into that surface. And the idea there is that geophysics tells you there's a magnetic anomaly or something that's there. So, you know, the decision to drill costs a lot of money. If you can triage your geophysical signals and say that, well, we're actually detecting metals there, we think that, or there is, you know, zinc or copper or something there that you can detect, it just gives it a little better chance to give you confidence to drill it. So here's Cross Lake. We've got, you know, kind of the rock here. It's got sand, it's got lacustrine, it's got, you know, wind-blown sand, it's got silt. As you dig down, you see varved layers. So as the glaciers went back, we've got kind of this 10 meters of fresh, new material that wouldn't have any metals in it. And the idea that you can just walk along the surface and run exploration programs. And certainly it's biologically active. You know, it kind of thaws out in May-ish, and it'll freeze up again in October, so you get maybe 4 months of good biological activity. Permafrost only goes down about 1 meter or so, so the stuff below the surface is going to stay active. It's not going to freeze. Okay, so you don't have to worry about kind of that softening down. The other is the Spence deposit in Chile, and this is Atacama Desert. So it's cold, it is extremely arid, and the idea here is that you've got a supergene system, right? Similar to Morenci, except it's buried, and your leaching material, you've got oxide, you enrich the sulfides, and then you've got primary ore below. And the idea here that you can walk along this stuff, which we would be generous in calling it a soil, and that there are geochemical signals within this that suggests there's something below. And again, the idea of minerals and materials getting to the surface. In this case, groundwater is a long way away. In the case of Cross Lake, groundwater was within, you know, probably, I don't know, 6 or 7 meters of surface, so fairly close to the surface that's there. One of the models that, you know, from back in the 80s was the idea that if you've got a large sulfide ore body, that it creates kind of an electrochemical gradient, like setting up a huge battery within the earth. And the idea there is that with fluctuating groundwater, and certainly as groundwater drops below, you can see, you know, like all of the supergene processes we talked about at Morenci would work. You could oxidize it, you make iron oxides, you make acid, and the idea that you have this electrochemical, and with that you bring water. So you're moving water around the system, and this idea that you'd have excess cations, and the cations we're talking about here is just acid, right? That if you're oxidizing sulfides, you're generating sulfuric acid, and you get these acid anomalies. Some of the geochemists who have done this work at Cross Lake and elsewhere have argued that, you know, you could run an exploration program with a little pocket pH meter. And then you'd just be going along and you'd just be measuring pH. That this cation concentration here going up would reflect a decrease in pH. And that wherever you see, you know, anomalous pH lows, and the key here is you're trying to target anomalies and very weak signals, that there's something going on below. It doesn't mean it's necessarily got metal, right? You can have, you know, lots of pyrite at depth that could produce the same anomaly that would be barren, right? It wouldn't be economic. So this is kind of the first go at this idea of deep weathering horizons, and in this case, cation diffusion to the surface. Other things that have kind of come into this is Stu Hamilton kind of expanding on it a little bit, and this idea that if you've got a reduced sulfide ore body, that as it consumes oxygen, remember you've got oxygen coming from the surface, so you've got gradients here that are going to push back and forth, that you're going to create a reduced column. Because it consumes oxygen, it's going to go anaerobic. And under anaerobic conditions, metals get more mobile. So that's a kind of a conduit for metals to head more and more towards the surface, right? Along with that, you're generating acid, So you're going to dissolve carbonate. Okay? Might not take it all the way to CO2. You might just make bicarbonate. And as that kind of goes out to the sides where you have less of an influence of acid, you can actually saturate and start accumulating carbonates on edges. So this idea, this acid anomaly, is that your pH might actually go up before it dips and then go up again. Go down. You've still got oxygen penetrating, so there's going to be a zone of metal accumulation, likely as iron oxides, right? And that if you target that, you should get at base metals in this case, zinc, cadmium, or copper, or whatever is in that deposit. And that it doesn't matter whether you've got what soil horizon or whether you're going through clay, that even as little as a few thousand years is enough, just with diffusion, for things to move up. Other things in arid environments they've looked at is the idea of seismic pumping, that as you have low pressure or high pressure systems moving over, you're going to move water and water vapor and potentially volatile metals. The volatile metals are fairly rare in most systems. The key though is that you've got to have some mechanism of getting metals to the top, and empirically they've shown that the metals that are from depth are getting to the surface. So here's Cross Lake pH. Scale is meters, so it's kind of skewed a little bit. So we've got kind of 20 meters in this bit. It's about a factor of 10 stretched this way, so it's not kind of a little bump. It's just a long hill that we looked at. But the pH here shifted almost 3 orders of magnitude between 2 and 3. So from a kind of a circumneutral to alkaline system up around kind of 7 and 8. All the way down to about 5.5, just above the deposit. So one criticism of this is that, well, you're kind of at a topographic high, and if things are draining a little more, then it's maybe more oxidizing, and that's why you've got acid, right? Because we don't have an absolutely flat terrain of homogeneous materials where you can discount every other variable that's there, right? That could explain why you're getting this kind of anomaly. One of the really interesting things they looked at was oxidation reduction potential. Okay, so this is your plus 400 millivolts. This is aerobic heterotrophs. You get down to minus 400. This is methanogens, methanogen territory. Iron manganese reducers, sulfate reducers, kind of in that successional cascade in terms of energetics. And when they looked at ORP at 8 meters, this idea that you've got maybe oxidizing edges, and acid conditions will help create oxidizing edges, but the idea of having a reduced column. So there is this idea of an influence of the sulfide at depth on the geochemistry of the water. And as they came closer and closer to the surface, it started shifting up. And that's reasonable. As you're coming up, within kind of a meter or 75 centimeters of the surface, you would expect there's going to be some influence of oxygen diffusing down from the atmosphere. So, within that soil profile, that redox should be shifting further up. And remember, these are averages. Right, like pH, you're going to get this average redox. There's going to be different reactions that can occur in this kind of environment. And when they got right near the top, so half a meter, and getting kind of into the soil horizon, we've got this oxidized cap. Okay, and if you're precipitating iron oxides and things like that, that would contribute to this oxidized cap. So this idea of this reduced chimney, making metals more mobile, reaching the surface, reacting with oxygen, and producing that oxidized cap that's a little bit acidic was perfect, and that was the kind of thing they were expecting. And it wasn't until they got to right within kind of the B horizon, which they thought would just be, kind of just almost this flat line right at the top, that it got really weird. And that was their ORP, 15 centimeters from the surface in that B horizon. And that's just crazy numbers. They went and bought a new probe and went back and measured it again. They thought they'd killed the ORP probe or something. So this is redox here, that's going all the way down to anaerobic conditions and up to aerobic and down to anaerobic. It's just the redox is fluctuating through that thing. And this isn't sampling on different days or it was raining that day or not. This is one afternoon where they went across this whole profile, but the redox is absolutely crazy within that environment. Now, from a microbial perspective, when you've got this kind of fluctuating redox, right, basically any reaction you can possibly write fits in there, right? Any reaction, any organism, every microenvironment that you could conceive of works within that B horizon of the soil. Completely took them by surprise. They didn't believe it at first. And this is what they're looking at, back to that same soil we looked at earlier, right? This is from Cross Lake, right? So it was this iron oxide here, and the samples there, and then they're like, just the, you know, the thickness of these layers, like they were, you know, and the whole idea is, do you pick a horizon that you sample? Do you pick a depth that you sample? In that study, they were picking depth. So, you know, if, you know, 15 centimeters is there, right, then they're near the bottom of it. But this isn't homogeneous, right? We've got this topography and everything that's there. So depending on one sample, you might be getting something up here or down here, right? So your sample medium can actually change. And then it came out of that going, you know, is depth really what they're going to be, should be looking for, or should you be looking for a specific horizon that you want to sample within any you know, kind of matrix or medium that's there. A couple of things that they've done, we'll look at the weak leaches, is this idea that, you know, do you take the whole horizon? If you've got metals that are coming up, zinc or copper, then should you sample closer to the bottom of that? And if we've got iron oxide in here, would you get better metal signals there? Or the idea that we've got, you know, we've got organic acids, right, leaching stuff down, the eluviation, that if you've got metals coming up and leaching down, should you sample at the top, right? So you've been collecting an awful lot of samples, and it's a challenging material to look at. Now, the leaches that you can use, and this is, you know, kind of goes back to the Brunswick camp as well, is this idea that the weakest leach of all would be just deionized water. Let's just take some dirt, we'll wash it with water, we'll see what comes off of it. Just metals that are absolutely soluble. That would be the mobile fraction, right? Hasn't stuck to bacteria, hasn't stuck to clays. Clays have negative charges. You can stick metals on clays. So this idea, there's Cross Lake here in copper at the Spence. You've got zinc at Cross Lake. So this idea of water as a leach. We'll look at the enzyme leach and MMI. These are two of the industrial weak leaches that are out there. Ammonium acetate, so this is the idea of targeting carbonates. So perhaps it would work better on the edges of these deposits. Certainly calcrete is a key target for gold exploration as well as other metals here in Australia, versus getting into like cold hydroxylamine. You know, that's, you read the literature and it says, well, it targets manganese oxides, and versus hot hydroxylamine targets iron oxides. And I look at iron oxides, you know, just that, and it's like, well, you know, are we talking fresh hydroxide, or are we talking hematite? There's a lot in this stuff here, you know, while it's a solid, it tends to have a lot of water, you know, it's much more reactive than hematite as a solid, or goethite in the middle, right? So there's real questions surrounding how specific these leaches are. That if you're adding a bit of acid, and this is kind of a pH 5 leach, that the acid that's there can pop metals out of iron oxides, or can pop metals out of manganese oxides. So it's not going to be absolutely specific. And then getting into a serious leach like aquaresia, you won't dissolve silica. You need hydrofluoric acid to do that, but you can dissolve gold with the aquaresia. So the enzyme leach, it's at labs. They're around the world. It's labs all over the place. And the enzyme that they're working with, so they're targeting kind of a sub 250 micron. They don't want bits of rock in there. They want fine-grained stuff, high surface area. They're targeting the B soil horizon, so that iron oxide as a material. They got an enzyme in there, and that's the base of their enzyme leach. It's a glucose oxidase. Oxygen goes into the reaction, and the idea here is you're producing gluconic acid. So you've got an organic complexation that's going on, but you're also producing peroxide, right, which is it's a serious oxidant that's in there. And the idea that this would bind, to zinc or whatever kind of metal that's in the system, and will solubilize it. And the idea there is that if you've got metals in the system, you dissolve the metals, so you get an anomaly, then it tells you something's there. Now within the B soil horizon, you're going to have organisms that can detoxify peroxide, right? But anything growing aerobically has to have these enzymes, including yourselves, right? You need catalase and peroxidase. Whether you're adding an energy or just using an enzyme, you're breaking down peroxide into oxygen or ultimately oxygen and water. Right, so they can be in there. But peroxide here, just, if you take an iron 2 solution or manganese 2 solution and throw in peroxide, you'll make iron oxide minerals and you'll make manganese oxide minerals. It is a great way, abiotically, to oxidize these things. So, this idea of dissolving a manganese oxide and producing a super strong oxidant as a byproduct, I've always kind of scratched my head, and I've spoken with the guy who runs the company, and it's like, what's the mechanism? He's like, we don't know, but it works. We're just, it's the empirical thing, right? It works, so we're going with it, right? We didn't really think of that, we're just thinking of an organic acid complexing, and it's working. So you go to Cross Lake, and remember, bottom here, meters, deposits over kind of about 20 or 30 meters or so. Different samples, remember? So B horizon samples, a lower B, so the bottom edge of it, and an upper B. So what do you think of enzyme leach? I got involved in a little bit of kind of geochemical exploration. And one of the things that's bothered me, and they're like, oh, you just have to get used to it, is this idea that you've got single point anomalies. You're going along baseline, ping, one sample, and then you're going along with baseline. And then you're suddenly going to tell them, well, spend, tens of thousands of dollars and drill this sucker. Just look at that. Right? This is great. Right? Versus, the upper B horizon here where it's like, geez, there's 5. Right? There is some latitude going on here. So, we're kind of getting anomalies from, kind of what, 160, 170, all the way over to 300. So there's some breadth that's going on there. So whether there's different mechanisms or it's just different seasons or, with that fluctuating redox, there's that much heterogeneity. One of the things that's been described is that you always know you're near an ore body because the sample spacing gets tighter, right? Because they've seen one and they're trying to get more hits, right? They've gone back and it's like, well, we've got one here. Let's go back, take more samples, and build confidence in the idea that you get a stronger signal.
The 1999 one, is that the data from the one that we were looking at before, the slide that we were looking at before?
Yeah, so this is Cross Lake, sorry. Yeah.
So that blue B horizon is the same data that we were looking at a couple of slides back.
Oh, no, so the
like
other
the
one was
15 centimeter one.
Yeah, so that was oxidation reduction potential. Yeah. So this is, sorry, we're Cross Lake, so it's zinc, and that's probably parts per billion.
Cool.
Okay, so this is a metal anomaly as opposed to an oxidation reduction potential anomaly. The mobile metal ion, it's launched in Australia, and it's the idea that plants accumulate metals. So whatever the chemistry is surrounding the rhizosphere should help mobilize metals. And so their proprietary technology is that they've modeled the rhizosphere in terms of pH or dissolved oxygen.